And you are of course most welcome. This is Project Euler problem number 24, Lexicographic Permutations. A permutation is an ordered arrangement of objects. For example, 3, 1, 2, 4 is one possible permutation of the digits 1, 2, 3 and 4. If all of the permutations are listed numerically or alphabetically, we call it lexicographic order. What is the millionth lexicographic permutation of the digits 1 through to 9? Okay, so as usual, brute force solution first, and then the elegant solution. So in the brute force one, we just we get itertools permutations from the Python library, and then we just keep counting until we get to the millionth permutation. So from itertools import permutations, we're going to have a function for this. So def p24 slow n. Right. Count equals 0, and then for p in permutations 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we do count. Do we do count plus equals 1? No, not yet. If count equals n, then we simply return the current permutation. Else count plus equals 1. And that's pretty much all we do. Now let's print out and see if we get the correct answer. So print p24 slow n. N in this case is not going to be 1 million. It's going to be 999,999. The reason for that is we already have the first permutation, so we want to go 999,999 permutations forward of this one. So n is that. We pop that in and let's see if it works. And it does. It's pretty quick. But we can go a lot quicker than this. This takes 1 million, well, slightly less than 1 million iterations to complete. Now, what if I told you that we can do this in 9 iterations? Yes, 9 iterations. This is how we do it. I'm going to set up my graphics tablet. I'm going to bring Paint onto the screen. I'm going to show you how this works. There's Paint. Okay, we need to move that up. There we go. Right, there's Paint. Right. So here's how it works. We start with our list. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got our list of integers, and let's say we want to find the 10,000th permutation. So this is the first permutation, so we want to go 9,999 permutations forward. So we start with a remainder, which is 9,999. So 9999. We begin by dividing by 9 factorial. 9 factorial is a lot more than 9,999. So we have a quotient which is 0 and a remainder which is still 9999. Now look at the quotient, it's 0. So we go to the 0th index in our array and we see that the value there is 0. So that is the first number in the lexicographic permutation. This is then taken out of the array. And we continue. 9,999 divided by 8 factorial. Now 8 factorial is 34,000 and something, so quotient again is 0 and remainder is 9,999. So we go to the 0th index in our array, which is the 1, and that is the second number in the permutation. That disappears. And we continue. 9,999 divided by 7 factorial. Now this time the numerator is bigger than the denominator, so we have a quotient of 1 and a remainder of 4,959. So the quotient is 1, so we go to the first item in the array, remembering it's a 0 indexed, so it will be this 3. This goes into the permutation and this is removed. We just keep going on. We keep going on until the remainder is 0. So there's a long way to go yet. So the remainder is now 4959. 4959 divided by 6 factorial. And that is 4959 divided by 720, which I think is 6, with a remainder of 639. There we go. So we now find the 6th item in our array. 0, 1, 2, 3, 4, 5, 6. It's the 9. That goes into the permutation and it's deleted. And we keep going. 639 divided by 5 factorial is 5 and 39, I think. So it would be 6. Yeah, 6. Yeah. So quotient is 5. Remainder is 39. So 0, 1, 2, 3, 4, 5. It's the 8. That is removed. And we keep going. 39 divided by 4 factorial, that is 1. Quotient is 1, remainder is 15. 0, 1, so we go to this 4. Put that in the permutation, that is removed. Keep going. So we have 15 divided by 3 factorial, which is 2, remainder it's 12, remainder 3. So second element, 0, 1, 2, that's the 6. That goes out and we carry on. What's left? Oh yeah, 3 divided by 2 factorial. That's going to be 1, remainder 1. Get the first element, that's the 5. Put that in there. 1 divided by 1 factorial is going to be 1, remainder 0. So now the remainder is 0, so we finish. But first let's get the first element from the array, that's the 7. That goes in, that's removed. And now we finish the calculation. There is one item left in our array, so we'll slap that right at the end. And this is the 10,000th permutation of those digits. Let's try that with the algorithm we have, just to make sure. So 0139 846 572. Can you see that? You can see that, that's good. Right. Let's have a go with, so I need to get rid of paint. There we go. I'll get rid of Chrome as well. Just wait a second. Right, let's get rid of Chrome. There. Good. Okay. So I just want to move this down so you can see the output. Just move it to there. That's fine. Right, let's see. Oh yeah, I didn't change the number. Oh, that one. So now you can see the answer. Well, there we go. So that is, I think, what we had. So that's the 10,000th permutation. So let's put that algorithm into use. I'm just going to move my graphics tablet, and we shall continue. Oh, hang on just a sec, drop my pen. There we go. Right. Move that back. Right. Def P24 fast. Oh, what have I done? Let's move that there. N. There we go. Okay. So we'll have an array with the numbers. So nums equals 0, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now f is going to be a factorial number. It's going to be the factorial of the length of the array minus 1. So f equals... Oh, we need to import factorial. Now the good thing about this solution is you might be working on a language that doesn't have iter-tools permutations. So the previous solution, as well as being brute force, it involved a library that you may not have in your language. So this new version is language independent. So from math import factorial. I'm importing factorial, but you can write your own factorial function pretty easily. So f equals factorial length of nums. Do you know what? I should just hard code that to 9. That's a bit of a waste of time. Just 9. Right. What am I doing? What am I doing? It's there. Right. Okay. So we need a string to hold the permutation. We'll just keep adding to it. And then while n is not equal to... What am I doing? While remainder is not equal to 0. So we're actually going to add in an argument called remainder there. So that's what we're doing. Right. While remainder is not equal to 0, then we'll actually do the processing. So quotient is equal to remainder divided by f, and remainder is equal to remainder mod f. Then we take the relevant digit out of the array and put it in the permutation. So perm plus equals nums quotient. Then we delete it from the array. And then we decrement factorial. So f equals factorial length of nums minus 1. Is there anything else to do? No, I don't think that's it. So right at the end we add the last item in the array to perm, so, and then we can return the array. We can return perm, which is a string actually. Right, that should work. Print P24 fast n, and this should work. It's gonna print out. We'll test it on the 10,000th iteration first, just to make sure it works. Oh, good thing. Oh yes, it's yeah. Got to convert that to a string because it's an int. So we'll just do that, and down there as well. There we go. Now try it. Yes, that seems to work. So let's try it for the big target. Yep, I'm happy with that. So that's it. And I will see you next time for problem number 25.